Today we're talking about escape velocities of various planets and moons. Can you tell us what a escape velocity is?
So, escape velocity is the minimal velocity you need to escape the gravity well of a planet. So, we have this nifty graph here. So,
Mm-hmm.
the blue sphere, it represents the Earth. The purple
Okay, yeah.
arrow represents a rocket trying to get away, trying to run away
Oh
from
my
the
gosh,
Earth.
you made it an oblate spheroid. That's accurate. It's
Hell
not
yeah.
Earth is not a sphere, it's a little squishy. Okay,
Yeah,
very
yeah.
nice, dude.
Because of the rotation.
Yeah, yeah,
Absolutely.
yeah.
And then if you notice, I made these little axes here. The vertical
Okay.
axis is gravitational potential energy,
Okay.
and the horizontal axis is the distance from the planet. And
Okay.
the red graph is the
Mm-hmm.
potential energy as a function distance from the center of the Earth.
I
So
see.
it's potential energy equals minus some constants times 1 over the distance. And this is valid
Okay.
for any distance greater than the surface. So we're going to ignore inside the planet.
I
We don't want
see.
to worry about that right now because we can't take a rocket off from inside the planet. A
From
current
from
tank.
underneath the planetary surface. Yeah, yeah. That thing's crushed. Yeah.
Yeah, yeah.
I guess my first question is why is this negative? We have negative gravitational potential energy on the surface.
Yeah, so I guess you have to set the zero of potential energy somewhere.
Mm-hmm.
And annoyingly, the most natural place to put zero is at infinity. We could make everything positive
Actually,
if we wanted to, but
oh no, no, that's worse. Because if we call it zero potential energy at the surface of the Earth and space goes on forever, then there's infinite potential energy somewhere far away. Like no, okay, okay.
right.
Somewhere far away, zero will be at a potential well and a negative gravitational potential energy on the surface. Okay, I'm happy
Yeah.
with that. Okay, I can
So
work
as
with that.
yeah, the closer you are to a planet, the lower your potential energy is, meaning the
Uh-huh.
more negative it is, meaning the farther from zero it is. That's how we
Hmm.
define it. So,
So it's like if we were to, I called it a gravitational potential energy well. So
mhm,
it's like analogous to like a water well. You gotta come up to get out of the well.
yeah,
I'm okay with that.
yeah. So I think
And
this
zero is like you're on the surface, you're walking around. Perfect. Okay, I'm
exactly,
down.
yeah. And in this case, the surface when you're outside of the water well is infinitely far away. In this case, that means you're out.
Infinitely super far away.
Yeah.
Okay.
So the way to find out this escape velocity is assume you start on the surface, and you've got to
Okay.
climb out of the energy well, the
Do, do,
potential
do,
energy
do,
well.
do.
So that means
Mhm.
assuming that you're not climbing on like a rope, but you're climbing by sending a rocket out, then you need some velocity close to the surface. So as you climb out of the potential energy well, your kinetic energy drops and drops and drops and drops until you get to infinitely far away where your potential energy is zero and the potential energy is zero.
So
And
you
that
said
would
the same
be,
thing twice. The potential energy is zero and also the kinetic energy is zero.
that's right.
Like you like stop at the infinity. Okay.
Right. Now, I guess you could have more. You could have plenty of kinetic energy above escape velocity, in which case,
Hmm.
when you're really far away, you'd still be moving. But we want to know
Hmm.
the minimum required velocity, or in this case, the minimum required energy to get out of the potential well, which is what escape velocity is the definition of. So that means
I see.
you'd have just enough kinetic energy to overcome the potential energy well. That's your escape
And
velocity.
not get sucked back in.
Yeah.
Perfect. I see it. I see it. So I think you've given us equations for this, right?
Yep. Yep. Can you walk us through
Hey,
this?
okay, right.
Yeah.
Yeah, yeah. So this is the escape velocity calculation. So we have kinetic energy subscript near. This must be at the surface of the
Mm-hmm.
Earth. And then your potential energy when you're near, and that's equal to the kinetic energy when you're far, potential energy we're doing conservation of energy.
Yep.
So we're gonna change the energy of movement into the energy of being far away from a planet. And
Yep.
you compare when we're near the surface versus when we're far.
Mm-hmm.
Okay. And so it looks like, yeah, yeah, yeah. Exactly as you said, the potential energy when you're far away, this thing approaches zero. It's going up to the zero on the axis, and then also stopped. So
Mm-hmm.
this is the minimum amount of energy. Okay.
Exactly.
And then kinetic energy, the equation is always 1/2 mv squared.
Yep.
And in this case, we're doing the far from Earth gravitational potential energy, which is this g, this gravitational constant,
Mm-hmm.
this capital M, the mass of the large object, in the case of the Earth,
Yep.
little m, the mass of your rocket, and then that's divided by the distance between the Earth, I guess center of the Earth,
Mm-hmm.
and the or surface of the Earth, and where the rocket
Yeah.
is.
I guess the R here
Okay.
is actually distance from the center of the Earth. But the r has
Hmm,
to be greater than the surface distance.
I see.
Yeah.
If your r is less than the surface, the equation just doesn't make any sense. We don't deal with it.
Yeah. There's a different form. Yeah.
Okay. Oh, hey, look, M. Yeah, okay, very nice. The
Yep.
M's cancel. That
Yep.
can be moved over, so it just doesn't show up here. And then you solve for V. So you take this stuff, shove it to the right side, multiply by 2. Hey, you got it. Very
Yep.
nice. And then square root it. That's the answer.
Yep.
Hey, that's easy.
Yeah.
And then some numbers. Hey, dude, you are thorough. For Earth, this velocity is 2. There's that 2
Yep.
times 6.67 times 10 to the negative 11. That's that gravitational constant.
Yep. Just gotta look that up.
And then mass of the Earth, about 6 times 10 to the 24th kilograms. Yep.
Yep.
And then the radius of the Earth. So this is the from the core of the Earth up to the surface.
Mm-hmm.
This is something many million meters,
Mm-hmm.
and it comes out to be this.
Yep.
Cool. 11.2 kilometers per second.
Yeah.
We should do a unit
That's
check.
so fast. Yeah. There's a unit check
you,
over here.
you did a unit
Did
check.
it.
Oh, so thorough.
Yep.
Okay, so velocity is. Oh yeah, there's a gravitational
Yeah.
constant, 6.67 times 10 to the negative 11th. It's meters cubed per kilogram seconds. And then you got the mass of the Earth,
Yeah.
kilograms divided by the distance. That's a m to the minus 1, meters to the minus 1.
Yep.
And let's see, m's, one of them cancels, kilograms cancel, second square, second round, square root it all. That's a meters per second. That's
There
a
we go.
velocity. Hey, very
Boom.
nice.
Yeah.
Very nice.
Can we look up on Wikipedia what the actual escape velocity is? Make sure I got that right.
Escape velocity, Earth. 11.2.
Ah, I'm off by
Very
0.1.
nice. What did we? Oh. Oh no.
No, that's
Can't
just-
trust
can't
can't
trust it.
trust you anymore. Okay, and look at this. Venus has 10.36, so 10.4 kilometers per second. That seems right because Venus is almost Earth-sized, but a little bit smaller.
Yep. But that
And then
makes sense.
Mars is significantly smaller because Mars is actually pretty small.
Actually pretty small, yeah. So it's a
I mean, it's still like a planet.
yeah. We get the radius is smaller, so you got to climb out farther,
Mm-hmm.
but the mass is significantly smaller because the volume to surface area ratio for spheres,
Mm-hmm.
the lack of mass wins. You know what I'm talking about?
Yeah.
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 Yeah. Well, that's escape velocity.
Cool beans.
Oh, the Wikipedia page.
If you want more information, that's where it is.
There it is. Yeah. All right. See you guys next time.
Next time.